In this, we are going to learn about the exponential function and its properties. So, what's the exponential function? A quantity like a to the b, where a is positive and a not equal to 1. We assume that a not equal to 1 to avoid situations like this. We know that 1 squared equal 1 to the cube equal 1 to 0. So things like that. But that can create issues later. So we can avoid that situation. So let's recall some of the facts about the exponential function. So for example, let's recall these. So how to find 2 to the cube? So 2 to the cube means 2 times 2 times 2. So you multiply 2 3 times, so you get 8. And then let's see what is 2 to the 3.5. So if you have a decimal number like that, what we're going to do, first we can write 3.5 as 7/2. And then this means that you're going to take the 2 to the 7th power and take half power. Half power means square root. So this is 2 to the 7 square root. 2 to the 7 is 128 square root. So if you calculate that, you can end up getting 11.31. So 11.31. So now, so that means if you have a decimal number like 3.5, something like that, you can see that you can convert that into a rational number, and then we can calculate that. Now the question is, what if you have something like this? So let's say 2 to the 3.2 repeats. So 2 gonna repeat. So and then we know that if you have a number that repeats, like for example 0.222 like that, you can write this one as a fraction like this. If you divide 2 by 9, you get 0.2222. So the same thing works like this. Let's say you have 0.333 repeating. This is simply 3 over 9. But 3 over 9 you can simplify. This is 1 over 3. So you can do something like that. That means if you have a repeated decimal, you can always divide by 9 and you can write it like that. Or sometimes if you have 2-digit repeating, like let's say 131313 like that, then you divide 13 by 9. So like that. So you can always do that. So that means you can convert a repeated decimal into a fraction. Because once you divide represent as a fraction or rational number, then you can do the same argument that we did before. So for example, this problem now you can do like this. So it's a 2 to the 3 uh, 0.2 repeating means is 2 over 9 as we discussed. So that means this is as a one fraction. You can write this one as 3 times 9 plus 2. That means 29 over 9. So this is simply 2 to the 29 and take the 9th root. So if you use a calculator, you can see that you end up getting 9.33. Okay, so that means we can do all of these like that. So what if we have 2 to the square root 2? So the problem is we know that the square root 2 is not a rational number. That means we cannot do this anymore. So what we can do in this case, we can use like a nice trick. We know that uh, square root 2 is approximately equals to 1.4142 like that. So because from advanced mathematics, you can show that if you pick any irrational number, you can find approximation that is close to, as close as you want to square root 2. So you can find like if you are given any irrational number, you can find rational numbers which are very very close to that irrational number. So that's you can show from advanced mathematics. So that means what we're going to do, we're going to use these numbers to approximate square root 2. So for example, instead of finding 2 to square root 2, we're going to do 2 to 1.4. The reason is, you know that as before, 1.4 you can write as a fraction. How? You can multiply the top and bottom by 10. You can write this one as 14 over 10. If you divide by 2, is 7/5. So it's 7/5. So that means, so using the same argument as before, you can see that this is approximately equals to 2.6390 up to 4 decimal places. Now what we're going to do, we're going to go one more approximation. We're going to say 2 to the 1.41. So again, you can convert this into also a fraction, because what you can do now, you can multiply by 100 now. So it's 141 over 100. This doesn't have common factor, so we leave it like that. That means it's again a fraction. That means we can do the same argument. So you can use a calculator and find it. So you're going to get 2.6574. And similarly, we can write this one as 2.1414. If you use a calculator, you're going to end up with 2.6647. You can see that 6 is fixed now, and then all three. So let's see what's going to happen when you have more numbers. So for example, if you have 2.14142, then you can see that if you use a calculator, you end up getting 2.6651. So that means you can see that the digit fixed now. So you see that 6 and 6 is fixed. So you can see that it's reaching a special value. So then we can write it like this. Now considering more and more approximations, you can finally say that 2 to the square root 2 is approximately equals to 2.665. So that is how you're gonna calculate a exponential function when b is an irrational number. So let's look at some of the laws of exponents. So we're gonna recall these properties. So laws of exponents. So as the first one, we're gonna go with a to the x times a to the y equal a to the x plus y. When you multiply, you add the index. So you look at the index and you're gonna add the index when you multiply. And then when you divide, so the second one, when you divide a over x and a over y, because you know that when you bring a term to the from numerator denominator or denominator numerator, it's going to change the sign of the index. That means you can write this as a to the negative y. Now this is like the first case, so you're going to add the index. That means a to the x minus y. So now you can remember, when you divide two terms with the same exponent, you're going to subtract the exponent. Good. And then number 3, we have you have product and to a power like this. So this is ax times bx. And then number 4, the same thing with division. So what happened? A to the x over b to the x. And then number 5, we have a x to the y. So it's a power of a power. When you have two powers like that, what you're going to do, you're going to multiply the two powers. So we can write this one as a x y. And then we have, this is something that we used earlier. So when you have a to the negative x, you can write this one as 1 over a to the x, or when you have 1 over a to the x, you can write this one as a to the negative x. So what do you remember, when you change from numerator to denominator or denominator to numerator, you can change the sign of the index. You can see, just change the sign of the index. So what is the sign? You can change the sign. And then we also have these two results. So we have 1 to any power is 1, and then as the last one, a to the 0th power equal 1 if a not equal to 0. So those are the properties that we're going to use when we work with exponential functions. So now let's talk about what we mean by exponential function. So let's write the definition. A function of the form fx equal a constant times a to the x, where a is positive and not equal to 1, is called an exponential function. So and then the base a is the what they call the growth factor and c is the initial value. Why we call this the initial value? And you can see that if you plug in 0, you can see that is c a to the 0, but we know that a to the 0 is 1, so it is c times 1, which is c. So so you can see that that is the value at 0. So when you have 0, so that's the value at 0. So that's why we call it the initial value. Good. And also we can notice one more thing. So what happens if you calculate f x plus 1? So you start with any value and you're going to calculate f x plus 1. So this is going to be c a to the x plus 1. Now what we can do is we can divide the two. So we can see what's the ratio between fx plus 1 and fx. So you can see that if you divide fx plus 1 by fx, so it is cax plus 1 over cax, and you can see c and c get cancelled, and then also ax with ax get cancelled. So that means you end up getting simply a. So what does that mean? That means that fx plus 1 is simply a times fx. So that means every time you move 1 unit, the function grows a many times. It's a times. So that means if there's a value at 0, so at the value a, it is going to be c times a. So whatever the value, it's going to be c times a. So every time if you go 1 more unit, it's going to increase by a times. That's why we call this is the growth factor. Call the growth factor, because it's going to increase by 1 unit. So we have so this is the definition of the exponential function. So before we discuss anything else, let's look at what is the shape of a general exponential graph. So let's look at some graphs of exponential functions. as a typical example, we're going to look at the graph of 2 to the x. So for that, what we can do, we can look at the table of values. So we can evaluate the function at let's say -2, -1, 0, 1, and 2. So so what is 2 to the 2? So 2 to the 2 is 4, and then 2 to the 1, which is 2, and we know that anything to 0 except 0 is 1, and then 2 to the -1, that means 1 over 2, and then 2 to the -2 means 1 over 2 squared, which is 1 over 4. Now what we can do is we can plot these values. So we have 0, 1, and 2, and then -1 and -2. So at 2 you get 4, and then at 1 you get 2, and at 0 it was 1, and then at -1 it is 1/2, and then at -2 it is 1/4. So now what we can do, we're going to connect the dots. So we're going to get this graph. So this is the shape of the exponential graph, and then you can see there are some special things. It is always passed through 1, and then it's increasing. So this is the graph you get when this is the graph of y equal ax when a greater than 1. You can see it is increasing. See, it is increasing. Good. So there are certain properties that such a graph has. So for example, we have, and you can see that this graph is all the values are always positive. So and then also let's start writing the domain and the range. So so the domain is, so domain is all real numbers. You can see it's defined for all real numbers, and the range is you can see is only non negative, like all the positive numbers. So it's from 0 to infinity. You don't get 0 or you do not get any negative numbers. So range is all the positive numbers. The domain is all real numbers, and then you can see that it passes through, so passes through the point 0, 1. This graph passes to the point 0, 1, that point. So that's one interesting property. And then so it is increasing. It's increasing for a greater than 1. And then you can see y equals 0 is a horizontal asymptote. Horizontal asymptote. So horizontal asymptote. So those are the basic properties of a exponential function for a greater than 1. And you can also see that the graph for other functions where a is greater than 1 have a very similar format, because it's just another number. For example, fx equal 3x have a very similar graph. So we can have this. So we have the graph of fx equal ax for a greater than 1 is similar to the graph of y equal 2x. So they all have very similar graphs. Only thing what happen is when a is larger, you get the graph, you get higher values. When the a is smaller, you get smaller values. So for example, we can draw these three graphs. Let's say we have the graph of y equal 2x, Now the graph of y equal 3x should looks like this. So you can see that both passes through the same point 1, and then so this is a graph of y equal 3x. So what happened when the values are larger, it's gonna move for the larger side, and this side is gonna go down. So so that's what happens. So it's kind of pivot at 1. So now what is the graph of y equal 1.5x? So you can see that when the values are large, they move, they get higher values on the right side, and values are smaller, the a is small. For example, 1.5, they are getting have smaller values. And on the left side is completely opposite. So what happens when the values are large is go down, and values are small go up. It's because it's 1 over. So that's the reason why that happens. It's like a pivot at the point 1. So just like at the point 1, it's kind of pivoting. So on one side is going up, the other side going down. Okay, so that's a characteristic of several graphs for different values of a. So now let's look at the graph of 1/2 x. So the graph of y equals 1/2 x. So you can see that 1/2 x, you can also write this as 2 to the negative 1x. In other words, 2 to the negative x. So we know that when you have a function like fx equal 2 to the negative x, so what happened here is you can compare this function with y equal 2x. So what happened? You replace x by negative x. So you replace x by negative x means this is a reflection about the y-axis. So you can see, so the graph of y equal to the negative x is the graph of y equal to x reflected about the x-axis, reflected about the y-axis, reflected about the y-axis. So that means if you use that fact, we can simply graph the y equal 2 to the negative x, just a reflection about the y-axis. So we start with the graph of the 2 to the x. So that has a graph like that, pass to 1, and it's going to go like that. So what we can do is we can reflect this graph about the y-axis, and you get this one. So this is the graph of y equal 2 to the negative x, because it's just a reflection about the y-axis. You can also get the same graph just using floating points. And you can see that this one is decreasing, so that's one thing you notice. It's a decreasing function. And also you can see the domain and range, they are all the same as before. So the domain is all real numbers. The range is 0 to infinity. 0 to infinity. And it also passes through the point 0, 1. So it also passes through the point 0, 1. And then the y equals 0 is a horizontal asymptote. So you have all those features for this graph as well. So let's try to graph like one special graph, but we're gonna do more graphs in a separate video. So let's do like a problem like this. So let's say graph y equal 3 minus 2 to the let's say minus 6, something like that. So so let's see, we're gonna do this as before, like go step by step. So we're gonna graph this one first using y equal negative x, 2 to the negative x, that we know. So that's like one of the basic graphs. So y equal to the negative x, and then y equal negative to negative x, and then finally we're going to get y equal 3 minus 2 to the negative x. So we're going to go step by step. So let's start with the first one. So that is one of the basic graphs that we know now. So is the graph going like that. So it's going to pass through 1. And then we have the horizontal asymptote y equal x, y equals 0. Horizontal y equals 0. Now, when you do the negative, it's going to reflect about the x-axis. So that means the graph of y equal negative to negative x looks like this. It's a reflection of that over the x-axis. And then what we're going to do is we're going to move this up by 3 units. That means you can change the asymptote. So that's the x-axis. So asymptote was at 0, but now it's moved to 3. This asymptote. It passes through 3. And also we can find what is the y-intercept. You can see y-intercept means you plug in x equals 0. If you plug in x equals 0, you get 1. That means the graph passes through 1. So finally, you're going to get a graph like this. So that's the graph of the function. This passes through 1. Good. So if you look at the domain of this function, so you can see the domain of this function is negative infinity to positive infinity. The range, you can see that it's going to get go from negative infinity to all the way up to 3, excluding 3. You can see that you never get the value 3 because that's asymptote. So this is y equal 3, which is an asymptote. So the horizontal asymptote is y equals 3, and there are no vertical asymptote. There's a horizontal asymptote in this case. So those are the values. So that's what you get for this graph. So let's try to solve. Let's try to look at a special value in mathematics. That's what we normally call the natural base, because here the you can see the in this problem the base is 2, but there are some special base called the natural base. So let's talk about that now. So there's a special number in mathematics we call E. That is defined using this quantity. So we can look at the values of 1 plus 1 over n to the nth power. So this quantity appears in many situations. For example, if you try to calculate the interest a bank gonna pay at the end of a year, they can use a similar expression like that to do. So let's look at several values of n and see what we're gonna get. So we're gonna go with n starting with 1, and then let's say 10 and 100 and 1000, 10,000, and maybe like a value like 10 to the 10. So and then if you calculate those values, and then you can see what you're gonna get for this expression, 1 plus 1 over n to the nth power. So you can see that when n equal 1, you get 2. When n equal 10, you're gonna get 2.5937 up to 47 places. And if you put n equal 100, you're gonna get 2.7048. If you say n equal 1000, you can see that in you're gonna get 2.7169. If you say n equal 10,000, you're gonna get 2.7181, and you can see that these digits does not change now. That means they are converging to reaching a particular value. And then if you say like a large value like 10 to the 10, and you can see that you're going to get a value like 2.718281, like that. So that particular number has a special notation. We call this is E. So that in mathematics we're gonna use this value as E. So it's approximately 2.718. That's what we use for most of the calculations. And this is called Euler number. So we call this Euler number. Euler number. So it's in the name of Leonhard Euler. He's a Swiss mathematician, and he's the one who found those this particular. He like studies a lot of interesting things. For example, he's the one introduced the sigma notation, the function notation for like writing like that, and then the I for complex numbers, and then E, the number that we just talked about. So all those mathematical notations are due to him. So this E is what we normally call the natural base. So we call this the natural base. Natural base. So for example, your function now we can write like y equal e to the x. So e is just a number. So this is roughly like 2.718 to the x. So that's the idea. So it's just a number. So there's nothing strange here. You can remember this just as a number. Okay. So we can probably graph a function like this now. So let's say graph y equal e to the negative x minus 3, something like that. So again, we're gonna go step by step. So we have y equal e to the x, and then we have y equal e to the negative x, and then y equal e to the negative x negative 3. So again, we can go step by step. So we know the graph of ex. So that's almost like y equal 2x. So pass through 1 and go like that. So that's number 1. Because e is roughly 2.7, so which is like close to 3. And then a negative x means you reflect about the y-axis. So the graph of the second one gonna look like this, reflect about the y-axis. Pass through 1. And then what you're gonna do is you're gonna bring this down by 3 units. So what's gonna happen is, so this one gonna go down by 3 units. That means you get a new simple. So this is at negative 3. So this is y equal negative 3. And then if you plug in 0, you can see that if you plug in 0, you get y equal 1 minus 3, which is negative 2. That means this the graph gonna pass through negative 2. So that means in this case you're gonna get a graph like that. So so that's the shape of the graph. So that is negative. So that's gonna go to infinity, and this is negative 2. That's a graph of So we're gonna see more graph in a separate video. That's only talk about graphing exponential functions. Okay, so now we're gonna next we're gonna focus on how to solve exponential equations. So let's talk about solving exponential equations. Solving exponential equations. So one of the major results that we use is equating exponents. So for example, we can see a situation like this. So if, let's say for some base a, so au equal av, because we know that these functions are one-to-one. Since the functions are one-to-one, because these are either increasing or if a function is increasing or decreasing, it is one-to-one. So those exponential functions are one-to-one. And because of that, if two quantities are equal with the same base, this is the same base, only thing can happen is u has to be equal to v. So that is the result you can use to solve a problem like that. And also, or you can say there's some base a, and then you have the same value. So let's say we have u, and also base b, you have value u. So if this is the case, only thing that can happen is a equal b. So those are the kind of results that we use to solve exponential equations. So let's try to look at several examples. So let's look at these two problems. So it says solve a 3 to the x plus 2 equal 81, b 4 to the 2x minus 1 equal 8 to the x plus 5. So let's look at the first problem. So a, so what we have is 3 to the x plus 2 equal 81. And you can see that those bases are different. So your goal is to bring it to the same base. So you can see, note that 3 to the x plus 2 equal, you know that 81 is 3 to the 4. So this is 3 to the 4, that's 81. Now you can see that they have the exact same base. So these bases are the same. Since the bases are the same, you can simply equate the index. So that means you can write, after this you can write, because the numbers are the same, bases are the same, so the index has to be the same. So that means you can write it, this one as x plus 2 equal 4. And then subtracting 2, you can see that x equal 2, and that's the solution. So you can see the solution is x equal 2. So let's look at the second problem. So what we have is 4 to the 2x minus 1 equal 8 to the x plus 5. And you can see that these two numbers are not the same base. So the goal is to bring it to the same base. But we know that you can write, you know that 8 is not a power of 4. But we know that both 4 and 8 are powers of 2. So we can use that fact. So you can say since 4 equal 2 to the 2 and 8 equal 2 to the 3, we can replace the 4 and 8 by powers of 2. So we can write this one as 2 to the 2 of into 2x minus 1 equal 2 to the cube into x plus 5. So we replace 4 and 8 by powers of 2. And then we know that power for power, that means a to the x into the y equal a to the xy. So because of that, now what we can do is we can multiply the two powers. So we can write it like this. So we can say, so this equals 2 to the, you multiply the two powers. So I say 2 times 2x minus 1 equal 2 to the 3 times x plus 5. After we do that, you can see they have the exact same base. So you can equate the index. We have, we can say equating index. Equating index. We have 2 times 2x minus 1 equal 3 times x plus 5. So that is the equation we getting using the equating index. Now we can distribute, so we're going to get 4x minus 2 equal 3x plus 15. If you subtract 3x from both sides and add 2 to both sides, you're going to get x equals 17. So that's the solution. So the solution is x equal 17. And you can plug this value and check that actually going to work. Okay, so let's try to solve another problem using exponential, using e. So let's say to solve, we can say e to the negative x squared equal e to the x squared times, let's say 1 over e cube, something like that. And then what we can do is, so if you get a problem like that, again the goal is to have the exact same base, and then you can equate the index. So what we're going to do, we're going to simplify the left hand side. So you can see that, so we have e to the negative x squared, this side is done, and here we have again power for power, so that means this is e to the 2x, and then if we bring e to the 3, you can write this as e to the negative 3. So if you simplify this, it's going to be e to the 2x minus 3. Now you can see that if you look at these two numbers, they have the same base. So that means the exponent should be the same. So equating exponents, we can write this one as negative x squared equal 2x minus 3. So now what we can do is we can bring all of them to one side. So if we bring all of them to one side, so I'm going to move everything to the right side. So you can simply write like x squared plus 2x minus 3 equals 0. Now what we can do, after we get this one, we're going to solve this equation. So solve for x. This is very easy to solve. We can look at factors, and you can see the factors are x plus 3 and x minus 1 equals 0, and then this simply says that x equal negative 3 or x equal 1. Now after you get something like that, you want to make sure that all those numbers works, and you can see that both numbers works in this case. So that means the solutions are x equal negative 3 or x equal 1. So let's have a short summary of what we did. So fx equal ax, so we have two graphs for a greater than 1 and a between 0 and 1, and there are several common properties. So the domain for both is negative infinity to infinity, the range is from 0 to infinity, and the intercept is 0, 1, and then y equal 0 is a horizontal asymptote, and then they are one-to-one functions. One-to-one function means inverse exists. We can talk about inverse exists. That's one property, and the second property is if a to the u equal a to the v, this implies u equal v, and also if let's say you have a to the u equal b to the u, that means this implies that a equal b. So that's the end of the exponential functions, and you can see more graphs in a separate video that's only about graphing exponential functions.